Gee SEDA, today I'm going to do a full walkthrough of how the SEDA token functions on the SEDA network in order to fulfill its three big functions on the network, which is number one, executing data requests. The only Oracle with an on-chain economy, SEDA, is the only Oracle network where its token is required during the execution of a data request. Only Oracle in the market that does it. Number two, securing the network, so its role with main chain validators and overlay nodes. And then three, there's a governance function. So before we dive into the actual token flow, here what you're looking at is the SEDA network architecture. So the purple is kind of the SEDA network, and then anything else is outside of the SEDA network that the SEDA network integrates to. So let's have a quick walkthrough top to bottom, bottom to top. Start off with any application living on any blockchain network. The reason that we can integrate with any blockchain network and provide data to any of their applications is because we have this little puppy here, is a proof of contract. The proof of contract acts as kind of the front door or the main door for communication between the SEDA network and any blockchain network. It's available in any blockchain language. And basically what it does is unwrap tamper-resistant proofs that are wrapped around SEDA data as it's shipped from the SEDA network by the solvers to the blockchain network. So it can read all the protected data from the SEDA network, and it's also the point where the application or a blockchain network will make its data request, which is monitored by the solvers on the solver network here. So we deploy the proof of contract. That's it. We're pretty much integrated. The only other thing is you need to point the solver to the proof of contract, which is super simple. And then, of course, yes, we have our solver network here made up of individual decentralized solvers. And, of course, there is a SEDA solver as well. They relay data requests to the SEDA network and results back. That's their big main function. You can build custom logic on top of those solvers as well, which is super cool on how you want them to relay your data requests or whatever. Then we have the SEDA main chain here, which is secured by the POS module of the Cosmos SDK and our main chain validators, which at the time of recording is around like 84. It's pretty sick. We have the SEDA burn address, which will come into play when we start talking about the token. And then applications or networks, they deploy Oracle programs that live on SEDA stored as WASMs. And so we can have as many of these as we need. And that's basically a container that contains all the instructions of how a data request must be carried out by SEDA. The reason this is so important is because as we only integrate with the proof of contract, so we can out-integrate any other Oracle where they're doing like, 3 to 6 months, 9 months, 12 months, depending on the Oracle. We're doing like 3, 6, 9, 10 hours. And we're deployed onto your chain. So huge and true. So because we're not integrating the whole network onto blockchain, we have these Oracle programs that live on the SEDA chain so that when you make a data request, the data request has an ID that matches your Oracle program ID, and we know exactly how to execute the data request. Cool. Then we have the overlay network here, which is made up of overlay nodes. Phase one, we've rolled out with professional overlay node operators. Most of them are main chain validators as well, but over time we will decentralize this even more so the community or anyone else who knows how to spin up a node can do so, with the end goal being tens of thousands of overlay nodes operational on your mobile device as well. We have a proxy node that lives for private data suppliers so they don't have to spin up new smart contracts and new connections for every API that they're offering. They just spin up a proxy node and then they plug their APIs directly into there. So it's one integration for a lifetime and they can offer any of their data. Of course, we have the public paid APIs and public free APIs because wherever there's a data source, SEDA can pull that data. Huge. SEDA token source is referring to sexes or dexes, and that will come into play now as we start to talk about what the SEDA token is doing during a data request. Cool. All right, so let's start up here with our applications living on any blockchain network. An application wants to make a data request. So it sends its data request via the blockchain network that it's built on to the SEDA proof of contract. Okay, so a data request comes into the proof of contract, which is monitored by our solvers here on our solver network. Now, what happens is that every data request has a value attached to it because there's operational costs, there's participation rewards, whatever it might be that's needed to complete that data request. So it living on the proof of contract, it then is monitored by the solvers here. The data request is coming through the proof of contract, and then the solvers essentially show the data requester their cost option for executing or delivering that data request to SEDA and then returning those results. Now, that's all done in any other currency that's not SEDA. So any other token could be USDC, USDT, or stablecoins, or native networks. But in this diagram, I'm just going to be using the USDC symbol, but it represents any other currency that's not SEDA. And basically what happens is once they have agreed on the terms and conditions of working together between the solver and the blockchain for the specific data request, the cost associated, the value associated is then sent to the solver in that currency. So it's the cost of the data request plus the solver's participation cost and fee for completing this on behalf of the application. So that goes into one side, into a solver wallet. And now what happens is, in order to relay that data request to the SEDA network, the solver must use an equal value of SEDA tokens to relay. So let's say in this case, one of these network tokens or whatever it was used is representative of 4 SEDA tokens. It uses these 4 SEDA tokens to fire the data request across to SEDA. And now what happens is a portion of the data request cost value is coming from CPU and gas. It gets burnt. So a portion of the SEDA, which is from the circulating supply, not from the minted supply, goes into the SEDA burn address, never to see the light of day again. Another portion of SEDA tokens go across to the overlay nodes, and we'll talk about what they do in just a second. And then another portion must go to the proxy node or to the private data supplier. In this case, we're assuming that the data is coming from a private data supplier. And now what happens is, as those SEDA tokens are being distributed to the burn address, the overlay network, and to the data supplier, the solver then, boom, relays the data request into the SEDA chain where it lands here, where the overlay nodes selected to participate, they read the data request ID, and the Oracle program ID is associated to that data request ID, and they follow the instructions which says, I want to query this data source for this data. That's the instructions that they follow. So they see, okay, we need to go and query this proxy node as defined in the instructions, and they want this kind of data. So they do so independently. They don't do it as a group. They all independently query this proxy node for the data, and then they return their reveals individually to a DR tally function, which lives on the SEDA network, which filters and reads how that data should be presented. So the overlay nodes are querying the proxy node, and then for that data to be available, obviously there's a value associated to that data from the private data supplier, so that's why they receive their SEDA token for doing so as well. Now, what happens over time, as we get more data requests coming through, the solvers keep receiving, whether it's stablecoins, native network tokens, whatever it might be. So this side of the architecture and the on-chain economy starts to fill up. And then, of course, what happens on this side is that for every data request, a bunch of tokens go to the burn address. For every data request, a bunch have to go to the overlay nodes. For every data request, a bunch has to go to proxy nodes for the private data suppliers. In the case of public paid APIs or free APIs, obviously free APIs, anyone can just query at any time, no problem. Public paid APIs, you'll need an API key for those, which the data requester can organize. We're building the Oracle program. So this is what ends up happening, is you have solvers that are accepting native tokens from any blockchain network or stable coins, and then they're sending off the SEDA tokens to the burn address, the overlay node, and the proxy node. And then suddenly they find themselves with lots of stable coins or native tokens, but they're out of SEDA tokens. So in order to continue participating in the solver network associated with the SEDA network, in order to keep participating, they should go to a SEDA token source in order to access more SEDA tokens so that they can continue their participation in the network. And the way that they would do that is they would effectively go to, I don't know, wherever it is, a centralized exchange, a DEX. They all have their own way of operating. They would put their currencies of their choice in, and they would get more SEDA tokens. And then doing so, they would be able to continue participating. And why is this important? This is super important because this creates the on-chain economy for data request execution. Solvers should, if they wish to continue participating, continuously take their accepted currencies from the blockchain network in that interaction, go and visit a SEDA token source, and then exchange those, swap those to access more SEDA tokens that they can then continue participating in the network. And then obviously this cycle keeps continuing. More SEDA tokens are burned, more data requests are coming through, more SEDA tokens are heading off to the overlay node network, and proxy nodes and private data suppliers are receiving what they need to. So this, in terms of data request execution, is how the SEDA economy, on-chain economy, functions. For every data request, SEDA tokens must be used in order to pay for the gas, to settle the gas costs, to settle the CPU costs, and that's burnt and put into a SEDA burn address, never to see the light of day again. Overlay nodes get their portion, and data suppliers get their portion. When solvers run out of SEDA tokens, they can use, through their own discretion, go to a SEDA token source, exchange, swap those tokens to get more SEDA tokens and keep on participating. So we end up with this really cool loop where SEDA tokens are always required to execute a data request, and for participation, those solvers must hold on to SEDA tokens as well. And so what you get in the end here is essentially a closed loop system. Closed loop systems are super important in ensuring a healthy on-chain economy and the ongoing execution of data requests.